Dear students, welcome to the knowledge series. Here we are going to discuss the backpropagation neural network and the concept related to the theoretical way how you are going to write in the university exams. So for the easy understanding about the backpropagations, you should see my previous video series on the backpropagations. Now here the backpropagations means that in a backpropagations the input sample which is being fed from the input through the hidden nodes to the output, it is being fed back to the input based on the error that is being identified at the output. That means the input layer, whatever we are feeding, it is being processed through the hidden layer to deliver at the output, and at the output it is being compared with the actual and the targeted vectors, and if the vector shows certain variations, based on that the weight adjustment is being carried out in the input to the hidden or a hidden to the output nodes, and thereby a further training is being carried out to in the feed forward conditions to see that that error is nullified. Now for the easy understanding, feed forward is a training, backpropagations is nothing but an error, and thereby finding a weight adjustment. Now let's see the backpropagations. Now as the backpropagations definition, it means that it is a central mechanisms by which the neural network can able to learn, and it is an algorithm based on the supervised learning. Thereby we apply the weight adjustment to see that the gradient descents can able to find a local minima, and thereby the error functions can be minimized so that the loss function can be minimized to an extent by adjusting the weights. Now here certain parameter is given for the parameter x parameter is given related to the input vector. T parameter is nothing but the target vector. Delta k we are defining with respect to the error at the output unit yk, and delta j is the error at the point zj. Alpha is the learning rate, and Voj is nothing but the bias at the hidden point. Wk is the bias at the output point, and Zj is nothing but the hidden nodes, and head Zj is a combination of x of I and Vij, that is how, and plus the bias, and Yk is nothing but the combination of Zj into Wjk plus Wok. So that is how we are able to find the Yk. So these are the basic parameters that carries out with respect to the network drawing. Now here some of the concept for this particular backpropagation is the first we initialize the weight based on random selections, and after that we do the network computations based on the input value and its weight, similarly the hidden and its weight in the subsequent output node, and that's how we do the summations as well as activation functions. Here also summation and activation functions, and do the feed forward. At the output of Yk we are going to find the actual output and the target output comparisons. That is the mean square error, and if that error is found, that error is propagated back for the weight adjustment. If we can able to adjust the weight, we will be able to find a delta of Ij is equal to alpha of delta k Vj, that is the new output weight output hidden weight which is ready for adjustment, and input hidden weight is delta of Vij is alpha delta j x of ij. So that is the delta, that is the new the weight with respect to the input hidden point. But for easy understanding, I have put it like this one. And how we do this adjustment? We minimize the total mean square error between the targeted and the actual, and that's how we compute the this weight, and this weight is being used to apply for the back propagations. And when we minimize the total square error, the output net value, it will go for the local minima. Now let's see the training part. Now training part is being stated in a very easy manner. Is that step 1. First we initialize the weight in a random conditions, and if the everything is okay, we can directly terminate. Otherwise, if we need to go for a training, then we have to follow these steps. What we do first, initialize, we collect all the inputs, and after collecting that input, we are sending transmitting to the hidden node. So in the hidden node, first it will take a Z of in. Z of in is nothing but the bias weight of hidden node plus summation of I is equal to 1 to n x of I, which is the input nodes, and it's a weight between the input to the hidden Vij. That's how once we get it, we apply for the activation functions. So we get a Zc, that is f of z in. So this is what we do the very first point of the calculating the hidden nodes. And from the hidden node, we are finding the y in k, where it is nothing but this z of j. It is coming here, and it's and between the hidden and the output weight, that is being multiplied, and it is being summed together with the multiple inputs plus bias of the output nodes. Then it will give us the z y of y in k. This y in k we are applying for the further membership functions. Once we apply for the membership functions, we are going to get the yk, just of like this one. How we are applying the activation function zz, we are going to apply yk is equal to f of y in k. So that's how we are able to get it. Now once we compute the both the node, that is in hidden node and the output node, the yk will be showing the actual output. This output is compared with the targeted, and if there is an error, then what we are going to do, we are going to apply for the for minimizing it, applying the total mean square error. So that is what we have done here. And to know about this computation, you see my previous video with respect to the back propagation. There I have elaborated about this one. So when we are trying to compute this delta k, that is the output in this is the step 7 is with respect to the output neuron. So in the output neuron, we are computing the delta k. What is delta k? That is the targeted vector minus actual vector and its activation functions. So that is how we are going to get it. So once we know this one, from this delta k we have to find the delta j. Delta j is nothing but the hidden nodes error. So delta j is the function of delta I in j of f dash of z in j. Okay. Now what is z in j? Z in j is nothing but the summation k is equal to 1 to n this delta k into wjk. So this wjk from where it has generated, this wjk is being generated between the hidden node and the output node. That is what we can see. So we have got two error. What is one error is because of the output node, another is with respect to the hidden nodes. So these two hidden node is there. So now we have to go for updation of weight. Now just see. Now here the output unit yk. we have know the output unit yk. So output unit yk has to adjust, look for the new weight. So what are the weight? The weight between the, if you look back, the weight between weight here, this weight as well as this weight. Similarly here, this weight and as well as this weight. So we have to do the look for the weight of output sections as well as for the hidden nodes. So that is what we are going to see here. So weight of the output unit yk, the correction term is delta of wjk. So delta of wjk is how much? That is learning rate into delta k into z of j. Z of j is the input from the hidden nodes. So that is, you have to keep it. That is the hidden node is coming. Now here the bias, what is bias? Bias is a function of learning rate and delta k only. So that is the this is the output side. Now once we know that one, we have to this is the changes that we try to incorporate. So these changes has to add with the old weights. Then only we will get the new weight. Similarly, this is the new change. So we have to add with the old bias. So that is what we try to see. Now here the new weight with respect to the hidden and the output link, that is the new weight is the old weight plus the corrected, the modified weight, updated weight. Now similarly the bias is also the new, which is the combination of the old weight and the new modified weight. So similarly we go for the hidden node. Hidden node also we are going to find the hidden node is the function of alpha into delta j into vj. What is delta j? You can see here delta j is the error which is generated at the hidden node. So that is what being there into x of I. So that is the x of I is nothing but the given input. That is what being stated, just like the previous case. And the bias correction term is nothing but that is the bias is the alpha of delta j. Now here also we do the hidden node also. This is the old hidden node weight. This is the modified weight of the hidden nodes link that combined together with the new weight of the hidden node link. So this is the bias, old bias plus modified bias. It will give you the this one, the new weight. Now once we get the new weight, with this new weight we further go for the feed forward, and after the training we are going to verify is the output is correct or not. If the output is appropriate, we can terminate. If the output is not appropriate, we continue the step. So that's what it is given. In the last test the stopping conditions for the minimizing of minimizations of error, and no further epoch is needed. So that's how when we talk about epoch, that means the total steps from the starting to the end for a one iteration, or how it follows, that is considered as a one epoch. So this is how we try to do the backpropagation theoretical analysis for the easy way of writing. So what are the stages? First you do the network drawing, then you write the parameters. After that you write the training step. In the training steps, all this first part training step, you are going to find the output, and from the output you are finding the error, and from error we are writing the updates. So that's how we write the backpropagations neural networks answer, which is one of the important questions, appears in almost all the universities across the globe. Now we will look across the numerical problem, because to understand the backpropagations a better way, the numerical problem is an essential content. That is how one will able to understand the backpropagation. So let's see the numerical problem. Of course, it has certain contributions, but you focus to this example, which is easy to understand. Now the problem is about to find new weights of the following neural network using a backpropagations. So this is you can see that one two layer structures where you are having one hidden node is there, followed by input and output. So that's why it is a two layer structure we are terming. So if you talk about input and output with respect to that hidden layer, so but otherwise you will say this is a three layer: input layer, hidden layer and output layer. So since here one single hidden layer is there, so we can able to use this example for understanding the back propagations. Now what are the variables here? Here the variables is that x1 is input, x2 is an input, z1 is the hidden, z2 is hidden, y is the output, 0 and 1 is the input values of the parameters at the x1 and x2, and x1 to z1 weight is given 0.6, here minus 0.1, minus 0.3, here 0.4, and at this point between these two 0.1 and between these two 0.4, and bias is given minus 0.2, here bias is given 0.3, and here bias is given 0.5. So that's how. And one important thing, the activation function is a binary sigmoidal functions. It is given. It's a straightforward. So you no need to worry about the derivative of a binary sigmoidal. So straightforward, a binary sigmoidal, you can take it. Now this is one table is being created. My advice is that you can draw this one and you fill it as the things progress. So here x1 and x2 is given. I have written that x1 and x2, 0 and 1. And the target requirement, we put it as a 1. That target, whether the particular target is what we are looking for. And we are considering the learning rate as a 0.625. That is the learning rate. Now the remaining all these things is you have to find. Okay, you have given only these things. So let's see how we have to start. Now dear students, you have to focus this that when we have to compute because this is the input, so first we have to compute Z1. So here if you see the hidden nodes, there are two hidden nodes, Z1 and Z2. So at Z1, one input comes from here, another input comes like this. And for Z2, one input comes like this, another input comes like this. At Y, it comes straightforward. So here you have to compute these inputs by first summing up here and then activation function. Here also summing up and activation function. That you have to keep it in your mind. Okay. So what are the three input? Here how many input is coming? Three inputs. These two plus bias. Here these two plus bias. Here these two plus bias. So three inputs all will be there always. Now here if you note it, it is written V11. V11 because this is 1 to 1. Here 1 to 2, 2 to 2, 2 to 1. So 1 1, 2 1, 2 1, and VO1. This is VO1, VO2, and W. So this is the our given input weight, and this is the input weight across Z1. This is the input vector at input vector at Z1, input vector at Z2. Now what vector? This is input weight vector. Okay, and W1 and W2 is here. This is the output weight vectors, W1, W2, W0. So that is being shown here. Now learning rate we have been shown here. Alpha is equal to 0.25. Now input is x1, x2, 0, 1. So activation function f of x is equal to 1 upon 1 by 1 upon 1 plus e to the power minus x. So everything is been written in the step 1. Now with this we have to start working. Now if you see the step 2, you have to calculate Z1. Now at Z1 what we are going to calculate? We are first calculating Z in J. Then we are calculating f of z in j. So then we will get z1. So like the same way, z in j, in place of j I am putting z in 1. So z in 1 is equal to x1 v11, x2 v22 and v1. That is x1 into this one plus x2 into this one, that is what, plus bias. So that is v01. So that is how we will get 0.2. Similarly, in z in 2 also we are taking this one, and we are having x1 and x2 we know, that is 0 and 1, and VO2 also we know it is here, and we have found here. So this is z in 2. So now we are going to find out z1. z1 is f of z in 1. So that is equal to 1 upon 1 plus e to the power of minus x means what? Z in 1. So e to the power 1 plus e to the minus 0.2, you get it 0.5498. So this is what you got in the first case with respect to the z in 1. Now similarly we are going to find out for z2. Now z2 we are going to find out. Now in the case of a z2 scenario, how we are going to find out z2? Z2 scenario is with respect to the case with respect to the same. Z2 is equal to f of z in 2. F of z in 2 is nothing but z in 2 is how much? Here we are get 0.9. Similarly, we are going to put 1 upon 1 plus e to the power z in 2. We are getting this value, that is 0.7109. So we have got two values, z1 and z2. Now what we are going to do is that we are going for a step 3. In the step 3, what we are going to do, since we know z1 and z2, so we have got this value and this value. Now we are going to find out y. Now first what we are going to find out y here? First we will find out y in, because y in is the summations of all the input vectors with respect to the weight, and then we are going to find f of y in. So that is what we have been shown here. So here we are going to find the y in, which is being given w0 plus z1 w1 plus z2 w2. Now once we know this one, we are going to find the activation functions. Y is equal to f of y in. So f of y in is equal to 1 divided by 1 plus e to the power of minus y in. So once we get this value, once we divide this one, we are getting this value of y as 0.5227. Now you have to remember that this is the output value. Now what is our target? We initialize target. You know that in our questions we are selected given that target as 1. So we are that is our target, but our target achieved is not this one. So what we do, we have to go for a back propagations. Now back propagations, first of all we are going to find a back propagations between output and a hidden node. That is why that is what it has been written here. You can see here. Now this is your output and hidden node. So once that output and hidden node we can able to compute, then we can able to go for the even the hidden node back propagation and delta k, delta g. So first we are going to find the delta k. Now how we find the delta k? You know the formula, and that delta k out is nothing but tk minus yk, target minus actual, into f cap, that is differentiations of f dash of y in k. So differentiation activation function of what is this one? That is f of y in into bracket of 1 minus f in. Now how we from where is this coming? If you go to the binary sigmoidal functions, and when you try to see the f cap of y in, there you can able to see this expression f dash of y in. So that is what I mean to say with respect to f dash of y in. So f of y in is equal to 1 minus f dash of y in. When you substitute this value of f of y in, you can see this one. F of y in is how much it is coming. This is coming as a 0.5227. That is what it is been shown, this f of y in. So that value you are putting down here, you are going to get f dash of y in. And that is what you are going to put down here, 1 minus 0.5227, target minus actual minus no, target minus actual. So when you compute it, you are going to get this value. Now once you get this one, what is the next? This value we are going to put down in the finding the delta Wik. So delta Wik is alpha into delta k into z of j. That is the weight with respect to the which we have discussed in the theory. Now once we compute this one, that is known as the change in weight. So we know alpha is how much? 0.25 given. Delta k is how much? Delta k is this value, and zj is what? Zj is the the input that we try to put. Zj is nothing but here is z1, because when we are finding out, we have to find out for two separately, so that and the error is created here. At this error we are giving these two inputs, so that's why we have to find z1 and z2. So we find for delta w1, and similarly we are finding for delta here once we find delta w1, we have to find for a delta w2 case also. So delta w2 we have to identify, that is what here it is being shown, delta w2. So delta 1 is that, delta w2 is there. Once we know this value, so we and plus delta w0 is nothing but a bias. So bias plus this is the link weight. These three is the new change in weight with respect to the hidden to the output node. Okay. Now similarly we are but this is not completed. We have to further proceed. Now we have to go for the backward propagations, that delta finding, and as well as the new change in the weight with respect to the input and the hidden node. So that is what I have written here, input and the hidden nodes, you can see. Now here how will you do? The same way, just like how we have done previously. For what we are going to find is that we know this expression is that delta z in j is equal to sigma k is equal to 1 delta k into w of w of jk. So this is our the normal expressions, and based on these expressions we are going to rewrite for the delta in of 1, delta in of 2. That means we are going to find a 2 hidden node delta. Now why we are going to find a 2 hidden node delta? Again you try to see here. Here we were trying to find for the single error is at the single node, but here error is at the 2 points. So you have to find at 2 node you have to find that particular error point. So that's why it is being shown here, delta in 1 and delta in 2. What is the delta in 1 combination? This one. So we have delta 1, we have to delta 1 into w of j1. So we are knowing that w11, these particular things we are aware about this one. But what is the delta 1? Delta 1 is the one error which is generated from the output nodes. So that is coming here. So that one multiply, that is delta 1 is here. That is what I mean to say, delta 1 out. So that delta 1 output is here. That is multiplied by the weight between the input and the weight of the output nodes. So that is a delta 1. And similarly, delta in 1, delta in 2 also we have got the output and the weight. So we have got this particular term. And once we able to know this is from these two terms, we have to find the next modification with respect to the weight finding, as well as with respect to the bias, that we will be seeing in the subsequent. Now this is the sections with respect to the one part. Now the other part we have to see, this one is that we are also writing that delta in J is nothing but delta in 1 into f cap of z in. That is the first part. This is the first part of the equations. Zj is equal to this one. You remember. If you don't remember, I will take you back to the theory. You just try to see this theory. We were talking about this is the output and this comes the hidden. So we are having this part and this part. We have done this one. Now we are doing this particular part. So that is what I mean to say. So once we compute for that second part, we will be able to know what is the value of f dash of z in f in, because f dash of z in, this is the value. This is a normal value which we know that how we are computed in the previous. This f of z in is we are knowing from the earlier figure is point, that is the output situations. In the output condition, y is equal to f of y in, how we have done. In the same way, the hidden nodes also we are having f of z in. So that value I have written, we have got this value. Similarly for z in 2 also, f of z in, we have got this one. Now once we know this one, here z in 1 and z in 2, these are the two weights we are finding. Similarly for the second node, we are also finding the two weights. Now what does it means? You try to see here again the network. Now if you try to see here, what we have found, here we found 2 delta. Now here how many delta? For this one 2 delta, this one 2 delta. That means 4 delta we are finding here. Now you can try to see here, there are 4 delta. That is what I mean to say. 1, 2, 3, 4. So that is what the 4 delta it indicates. Now once we know this 4 delta, what we are going to do, we are going to, this is the change in the hidden node weights, hidden node weight with respect to the Z1, and another way, another node we will getting with respect to Z2, a change in weight. Now everything we know, everything we got, the delta we got. Now what we have to do, we have to compute the final weight of the network. That means we will be computing Vi nu is equal to V in all plus delta V in. So we have to add all the delta V in together. So how many inputs changes will be coming? If you note it, the total 9 changes will be you are going to incorporate in this particular case. So you are going to write what are the new change in weight. That is V11, that is x1 to z1. This is V1 to x1 to z2. This one V21, x2 to z1, x2 to z2, x2 to z2. Then your W1 is with respect to z1 to y1, W2 z2 to y2. Then VO1 bias, VO2 bias, and WO bias, hidden bias and as well as output wise. So that's how we update all the outputs. So this is what means the back propagation numerical. So what you have understood is that the problem is a straightforward. There is nothing confusions. Only you have to remember that first you have to add the identify the Z1, Z2 and its Y, and after that you find the error. Once error is known, you apply the error equations for the output node. It is a delta k, that is a tk minus yk into f dash of y in k, and for a hidden node you write it delta I in j is equal to sigma k is equal to 1 delta k wjk, and zj is equal to z in j f dash of z in j. And with that you identify the new change in the weight you will write with respect to alpha into delta. If it is output in the theory I have mentioned, wjk is equal to alpha into delta k into zc, and if it is a bias, delta WOK is equal to delta into ZK. There is nothing you have to put with respect to additional inputs, because ZSO itself is 1. And similarly, in the case of input hidden node, alpha, we write is alpha delta j x of I, that is the input to hidden, and its bias delta VOJ is alpha into delta j, where again we consider the x of 0 is equal to 1. So that's how we do, and finally we add WJK new is equal to WJK old plus delta JK, and VIJK new is equal to VIJK old plus VI. This is how we complete the back propagation. Now finally, before we conclude, let us see some of the application. The application of the neural network is being diversified into various fields. Aerospace is there, automobile is there, military, electronic, medical, industrial, telecommunication, transportation, machine learning, ANN. Now basically, in one word, I can, considering all together, if I take into considerations of a machine learning, the classification is one of the area where the neural network plays a very major roles to recognize the handwritten characters or a face recognitions. All these things is possible with the help of a neural network. Even in the signal processing, the neural network plays a major role. Speech recognitions to identify the voice or the speech language, or a speech to text converter, or a text to voice signal converter. All these things is a part of a neural network. Pattern recognitions, handwritten, as I told you, speech, printed characters, all these things is a part of the neural network. For example, you can able to forecast, and if any risk is taking place, neural network plays. You talk about transportations, say driverless car, the neural network plays a major role. In the medical field, the neural network contributes majorly in identifying and doing testings. Today, now is the COVID-19. There are several machine learning algorithms works on the COVID database. You can see there tremendous and deep learning computational is being carried out to identify the analysis about the different cases. So that is how the contribution take place. In the financial forecastings, the neural network can able to find the dynamics of the market. Even as optimization, there are various optimization tools is being used for research purpose, so that those tools can able to identify the problems and can able to optimize to give a best outcome. Even the best model can able to generate for future testing. Even neuro forecastings, when I say neuro forecasting, the neural network is basically used to predict or can able to predict a long-term that is our market or a foreign exchange rates, and how the market is going to vary as compared to the various situations. Even in the present COVID-19 situation, how the market will be after a year or after a certain period. All this thing is possible with the help of strong computations. In a conventional computation, this is not possible. However, with the help of neural network and the deep learning, it has brought a tremendous changes in the computationals. And condition monitoring systems. For example, I mentioned here in the case with respect to the aerospace or with respect to the industries, all the sensors and its measurement, as well as how it has to monitor the various control functions. Everything is possible with respect to the neural network. So, dear students, I believe that we have covered a lot with respect to the neural network. And neural network has given a way for the soft computing. It has reached made the much heights with respect to the design development, as well as able to contribute. A lot of research is still and every day continuously work on this particular area. So I believe that with this I conclude the discussions with respect to the neural network under the back propagations. Thank you.